14.5 is solving trig functions. I think I'll make two videos actually, one when we solve basic ones, then as we get more complicated I'll make another video. Basically we're trying to solve for theta. Our goal is always to get this variable, x or theta or whatever it is, to get that by itself. You'll often be given a range of some sort, something that tells you what theta can be between. Right now we're saying theta is between 0 and 360, and it can't actually equal 360. It can equal 0, it can't equal 360. We've got to find some theta, and in fact every possible theta, between 0 and 360, where the cosine of theta gives us 1/2. Well, there's two ways to do this. One way is to just look at your unit circle and see where the cosine value, see where the x value is 1/2. And that happens here at 60 degrees and here at 300 degrees. You'll note those are reference angles. They're always going to come in these pairs of reference angles. So our solutions would be theta equals 60 or 300. Both of those fall between the domain that we're restricted to. But the other way to do this, especially if the thing you have isn't on the unit circle, is to do a cosine inverse. The inverse cosine of 1/2 is 60. The problem with your calculator is it can only give you one answer. The answer it gives you for sine, when we're doing cosine, the answer for cosine will always be in quadrants 1 or quadrants 2, because that's where cosine is positive and negative. So cosine only comes out in quadrants 1 and 2 in your calculator. Sine is only quadrants 1 and 4, because sine is positive and negative here, and tangent, I believe, is also 1 and 2, but it might be 1 and 3, I can't, or 1 and 2 or 1 and 4, I can't actually remember. It doesn't really matter, we'll figure it out when we get there. So, cosine of theta is either 60 degrees or 300 degrees. Well, here's another one. 3 sine theta plus 4 equals 1. I want to get the theta by itself, so I'll subtract a 4 from both sides and do algebra. So I have 3 sine theta equals -3. Divide everything by 3, and I get that the sine of theta equals -1. Well, here I have to be in quadrant 3. That's what this is saying. If I'm between 180 and 270 degrees, think about which quadrant you're in. You have to be in quadrant 3. Well, where is the sine of theta -1 in quadrant 3? Because I'm allowed to include 270, it's less than or equal to, that happens here at 270 degrees. If you wanted to check, you could do the sine of 270. I'm sorry, 3 sine 270 plus 4. 3 sine 270 plus 4 is 1, and that's what I wanted. And of course we could have done sine inverse. If I do sine inverse of -1, that gives me a -90. So it's thinking about it like in quadrant 4, but -90 isn't within our region. -90 isn't between 180 and 270. So I have to take that and put that in quadrant 3, find a reference angle or find a coterminal angle and put that in quadrant 3, so it's 270. Finally, where's sine of theta 0.25? Well, that's a quarter. 1/4 isn't anywhere on this circle. None of these values are a quarter. So I have to think about this. I'll do my inverse sines in the option here. So theta will be the sine inverse of a quarter. Sine inverse of a quarter. It's 14.5 degrees. Well, here's where this gets a little bit tricky. I have to do this for every possible theta. So that means it could be 14.5, or I could go around a circle and be at 374.5, or go around another circle and be at 1134.5, and I can keep adding on 360s and 360s and 360s, and keep going around by as many circles as I want. So the way that we show that is we use our trusty little letter K. We do 14.5 degrees plus 360k, where k is any whole number, or any integer. And that accounts for having like 2 circles or 12 circles or -3 circles, but going around over and over and over. And that gives us most of the values that work. And here's where those reference angles are so important. 14.5 degrees is here. This is 14.5 degrees. And I'm doing sine. Well, sine is positive in quadrants 1 and in quadrants 2. So I have to think about this angle here at 14.5 degrees. And if that's 14.5 degrees, this little chunk here was 14.5 degrees, this whole angle here is 180 minus 14.5. And 180 minus 14.5 is 165.5. Plus all of our revolutions, plus all those circles. So just like how problem 1 had 2 solutions, 60 and 300, this third one has 2 solutions, and we have to account for every single possible theta that could give us a sine of theta at 0.25. If you think about the graph of sine of theta, you know, a graph shows all the possible solutions. Oh, I just broke everything, I think. Fix that. If you think about the graph of y equals sine theta or y equals sine x, it looks like this. It goes up and down and up and down, up and down. Right now I'm counting by 90s. There's 90, 180, 270, 360. And I'm counting by 0.25s actually along the y-axis. So there's negative 1 right there at 0.25. Well, if we think about graphing the line y equals 0.25, this chunk right here, if we graph the line y equals 0.25, we'll see it crosses it many, many, many times. There's a solution here and 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 here. And basically every period, every time the period goes around from here and it cycles through to here again and cycles through to here again, every time you go through one period, you are going to hit one of your solutions. And that happens on 2 times. Happens kind of on the way up on the curve and the way down. So a solution here, you travel a period and a solution there and there. So there's these 2 solutions that move by the period of 360. If the period were to change, so would the amount that we changed the variables by. So that all comes down to reference angles. I know that reference angles weren't always our best friends, but we can find this little piece here, which lets us really find this big piece here that we care about. Okay, I'll move on. On the left side here, I'll do some simple problems that aren't trig to kind of get us ready for the more complicated trig problems. This problem has 2 x's, one of them is squared and one of them isn't. So I factor. I can pull out a 3x and I'm left with x plus 1 equals 0. So my solutions would be 3x equals 0 and x plus 1 equals 0. So one solution is 0 and one solution is negative 1. I'll do the same thing over here. This has 2 variables, basically. Think of sine squared x and sine x like it's basically x squared and x, only with signs on them. So I factor out a sine x, and I get sine x times sine x plus 1 equals 0. Well, that I factored, I take my 2 factors and set them equal to 0. So I have sine of x equals 0, and sine of x plus 1 equals 0, and I solve these. If sine of x equals 0, on the unit circle, that happens twice. That happens here and here, at 0 and at 180. And then it'll happen again at 360 and 540 and at 720 and 1080. And it's basically at 0 counting by 180s. So x would be 0 degrees plus 180k, where k stands for any integer. Here, sine of x plus 1 equals 0. So sine of x is going to equal negative 1. And where does that happen? That happens only at 270 degrees. That's where the y value is negative 1. And there's no other times, just then. So this is just going to be 270 plus 360k. And if you're wondering, why did this have a 360 but this had a 180? Well, when sine equals 0, it's actually moving from 0 to 180 to 360. It just keeps going by 180s every time. It's counting by 180s. What I could have done is I could have said x equals 0 plus 360k, and that's one of my solutions, 0 plus 360k. And then I could have said x equals 180 plus 360k, and that covers both of the possibilities. But since 180 is just half of 360 anyways, we just said it's 180k. or 0 plus 180k is actually redundant. I could have just said this is 180k. Okay, over here I've got letter u's, just like x's but different. And you actually see u's in trig sometimes. This is a quadratic that needs to be factored. I could do the quadratic formula if I'd like to and find my values for u here. In fact, maybe I'll show that later. But this factor is really nice. It's 2u minus 1, u minus 1. And that equals 0. I found two numbers that multiplied to 1 and added to negative 3, knowing that this first number here is 2. And that first a value can make things tougher. When I solve this, 2u minus 1 equals 0, and u minus 1 equals 0. So u equals a half, and u equals 1. I'll play the same game over here. I want this to be equal to 0. Factoring and the quadratic formula only work equal to 0. And it's going to factor the same exact way. It's basically the same problem. This structure here is the same as this structure here. So I'll have 2 cosine theta minus 1 and cosine theta minus 1 equals 0, and I solve both of these. Well, where does cosine theta equal a half? So I add a 1 to both sides, so 2 cosine theta minus, or equals 1. Excuse me, 2 cosine theta equals 1. So cosine theta equals a half. Well, where does cosine theta equal 1/2? Hopefully at this point you've kind of got that memorized. I'm doing this in radians. That happens at pi over 3 and 2 pi over 3. Let me check to make sure. Ooh, nope, not 2 pi over 3. That's definitely not right. Let's pull up the unit circle and see. Cosine theta equals 1/2 at pi over 3 right here, and at the reference angle of 5 pi over 3. So it's at pi over 3 and at 5 pi over 3. Those are my two solutions. Now the period of this function is 360. So I really want to have both of these be plus 360k, which is 2 pi. My period is 2 pi. And that was just me solving this one. Now I've got to solve this one. I want cosine theta minus 1 to equal 0, which means that cosine theta equals 1. And cosine theta equals 1 only at 0 degrees, or 0 radians. So that's 0 plus 2 pi k. In this case, this is every single possible solution that would solve this equation. Now what some people prefer to do is to get rid of the cosines entirely, because that kind of throws them off. And that's when you can do what's called u substitution. I can take u and say that equals cosine theta. Set up the equation u equals cosine theta and replace these cosine thetas with u. Then you solve, and when you solve, you'll get u equals 1/2 from here, and u equals 1. Then go back and plug those u's back in, so we get that 1/2 equals cosine theta, and that 1 equals cosine theta. And this is kind of just a head game. You would then solve this from here, you'd go on. Kind of just a head game to not have to deal with the cosines yet. Just basically, let's get rid of the cosines, let's make it some u, and move on from there. You'll actually need to do this later in places like pre-calc and calc, but it's a good thing to get familiar with here. Okay, we'll just do a couple more examples. This time I'm only going to go in one circle, 2 pi. I know I'm doing this in radians because it gave me a pi. I can factor a cosine out of this. Factoring is a really good friend of yours in this. Factor a cosine, I'm left with sine minus 1. So I want cosine of theta to equal 0, and I want sine of theta minus 1 to equal 0. Well, cosine theta equals 0 at pi over 2 radians and at 3 pi over 2 radians. And that's everything between 0 and 2 pi. Sine of theta equals 1 at 90 degrees, or also pi over 2 radians. In this case, these two things overlap, and that's fine. Your solutions are pi over 2 and 3 pi over 2 radians. Suppose you want to do this in your calculator. So suppose you take cosine theta equals 0. And you want to plug that into your calculator. So theta equals the cosine inverse of 0. Well, when you do that, if your calculator is in radians, which it needs to be because this problem's in radians, so I'll switch this over to radians. When I do the inverse cosine of 0, it gives me that, which isn't very helpful. But what you can start doing is kind of getting clever. You know that a radian has a pi in it somewhere. You know, like this was pi over 2 or 3 pi over 2. So what I can do is divide out the pi. If I divide the pi out of this, it'll show me the fraction that's left. That was 0.5 if I want to make that a fraction. Oh, there's really 1 over 2 with a pi, so 1 over 2 pi. So you can always try and kind of find your pi values and find your radians by dividing the pi out of a decimal whenever you're given one. One of the more useful tricks I know with those calculators. Okay, last two. Tangent now. Remember, tangent has a period of 180, not a period of 360. Period of tangent is 180. So I solve this, I get that tangent of theta equals negative 1 over 3. I'm not really skilled enough to look at my unit circle and find that. So instead what I'm going to do is just do the inverse tangent. This is going to be in radians. Let's do it in degrees. The inverse tangent of negative 1/3 is negative 18.4. So theta is going to be negative 18.4 degrees, which makes sense because on the unit circle, tangent is negative here and here. What's really, really nice about tangent is all you have to do is add a single period. So if I want to find every single possible value, I would say theta equals negative 18.4 plus 180k. And just take whatever your first answer was, add a period to it. In this case, the period is 180, and that gives you every single possibility. So 3 tan 2 theta plus 1. This is kind of the first tricky-ish example we'll come across, and then I'll stop. Well, I solve this, so tangent of 2 theta equals negative 1/3. So I do the inverse tangent. 2 theta equals the tan inverse of negative 1/3. Did I just do that? I did, negative 18.4. So we get that 2 theta equals negative 18.4. Well, I divide both sides by 2. And theta now equals negative 9.2. So my solution is negative 9.2, and then I want to add on a period. But the period of this function is not 180. The period is now 90. Because remember, it's 180 over b. And this is the first time we've had a b value of anything besides 1. So the period is 180 over 2, which is 90. So I would do plus 90k. And then the beauty is I could check that. You know, in my calculator, I could type 3 times the tangent of 2 times, let's do negative 9.2 plus 180. Because that's like 90 times 2 is 180. I'm going to plug in 2 more periods. And then I add 1, and hopefully this comes out to 0. Basically it does. Yeah, because of some rounding, it's a little bit off, but it's going to come out to 0. There we go. There's your first video. I'll make another one that handles some more tricky issues, but this should take care of the start. Thanks for watching.